Okay, for this video, you're supposed to do the questions for your HBL. Okay, sorry I've been late in uploading this video. Okay, so the question that you need to do is question 4, MCQ. Figure below shows a current carrying wire. That means the wire has current flowing in it, and it is placed in a magnetic field. Okay, so the magnetic field is going in this direction. Okay, current is coming out this way. That means if I were to transform it into a 2D, let's say if I were to put my eye here, okay, I would see this conductor and then it will be a dot. So this dot is actually representing the current, okay? And since I look at it in this view, the external magnetic field is going from left to right. Okay, so these are the external magnetic field. So they want us to find the direction of the force experienced by the wire. So the force can only be happening when the current produces a magnetic field and it is placed in an external magnetic field, right? So due to the interaction of the magnetic fields, there will be a force. So for this, we need to apply Fleming left-hand rule, or we can draw the magnetic fields and see where we have more magnetic fields. Remember the 101 or 121, whereby we examine where we have more magnetic fields. But for this, I'm going to just be using a Fleming left-hand rule. So for my current, I'll be using my middle finger, which is the I. So if I'm facing it this way, my middle finger will be pointing towards me, and my first finger will represent the external magnetic field. Okay, so something like this. Okay, so this is my hand. Okay, this is my hand. Okay, so this is my force, this is my external magnetic field, and this is the current, right? And therefore the force will be going up. That means answer is B. Okay, I hope you haven't forgotten this. Okay, the next question that you are supposed to do is question 7. So now we have a wire passing through the poles of a horseshoe magnet. That means my horseshoe magnet is my external magnetic field, right? So there's a current in the wire. So the current in the wire produces a magnetic field, right? And it is interacting. So this magnetic field that the current produces interacts with the external magnetic field. Then there will be a force. Okay, so there must be first current flowing. When current flows, it will produce magnetic field. And if it's placed in an external magnetic field, they will interact. And then there will be a force exerted on the current carrying wire. Okay, so in this case, they are giving us the force. They give us the direction of current as well, and they also give us the external magnetic field, which is going from north to south. Okay, external magnetic field is always going from north to south, and in this case the force is downwards. Let's try with Fleming left-hand rule. So you need Fleming left-hand rule to determine the direction of the force, and I can confirm with my Fleming left-hand rule. So in this case, this is my hand that I'm drawing. Okay, this is my first finger. My middle finger is pointing this way, and my thumb is pointing downwards. Okay, so because it is pointing towards into the screen, right? This is my current. Okay, so I can conclude that the force is indeed going downwards. Okay, now we have 3 other arrangements. Okay, magnet is turned around, direction of current is reversed, and direction of the current is reversed, and the magnet is turned around. Which arrangement will cause an upward force to act on the wire? They now want an upward force. So actually it doesn't matter. We don't even need this diagram, right? Because over here they just need an upward force. So if I were to do, P will get an upward force. Remember to use Fleming left-hand rule. Q will also be an upward force, and this will be downward force. So only P and Q. So answer is C. Okay, so I don't know why they need to give us this diagram. Okay, so let me see. Question 7, answer is C, right? Next one is question 8. Okay, it's also should be using Fleming left-hand rule. Now let's look at AB. maybe again I draw it in 3D view. Let's say my eye is looking at this way. Okay, so I will see AB over here. I will see CD, right? And the current is coming towards the eye, right? For AB. For AB, the current is sort of moving into the eye. So it will be a dot. For CD, the current is going away from the eye. So it will be a cross, right? Dot means coming towards you. Cross means going away. Okay, so now that I have this and I have current flowing in the wire, okay, current flowing in wire, I have external magnetic field going from left to right, north to south. Okay, so now I can determine the force acting on AB. Let's do AB first. So your middle finger should be pointing towards you, north to south, so your first finger should be going from left to right. The force will be vertically upwards. Then for CD, because the current is changing direction, but the external magnetic field is still left to right, so the force is going this way. Therefore, it will be a clockwise moment. But they say when viewed from the side AD, that's where I place my eye. So answer is D. Okay, let me double confirm the answer. Okay, sorry for the pause because I checked the answer. Answer is wrong, but I'm pretty sure answer is D. Okay, so please verify. Help me verify. Okay, so that's all for the MCQ that you're supposed to do. Okay. Okay, I'm not sure if I asked you all to do question 9 or have I gone through question 9 already. Okay, but maybe I'll go through question 9 now. Okay, so basically there's a bar. It's a metal bar. I'm not sure whether is it magnetic material, but there is a north over here. That means my compass is pointing in the correct direction. Okay, but once a magnet is brought near this bar, the compass direction is reversed. Okay, that means now it is because the tip of the compass is a north, so here will be a south. Then my X is supposed to be a north, here will be south, here will be north, and this is south. Okay, so this is the only arrangement. So whether the bar is it a magnetic material or not, it doesn't matter because the magnetic field lines can pass through it. Okay, can influence the compass here. So the unknown magnet is made of magnetic material such as nickel is possible. Okay, it's made of a non-magnetic material is also possible. Okay, because regardless the case, the magnet can change the direction of the compass. Now, the unknown bar is a magnet with X as the north pole. This is not possible because of the initial position. Because for compass, right, the tip of the arrow is the north pole. So if X, they propose that it's a north pole, then by right, this direction will change. Okay, but it didn't change, right? Therefore, 3 is not possible. So answer is B, 1 and 2 only. Okay, question 10, I think I didn't ask you all to do because actually they didn't talk about the split ring commutator in much detail for your syllabus. But I think we can try this. So in this case, the split ring commutator is left out. What is the function of the split ring commutator? It is, please write this down, reverse. It is also in your notes. It will reverse the direction of current in the coil so that every half a revolution, okay, which is actually 180 degrees, so that the coil can continue to turn in one direction. Okay, so if my split ring commutator, the function is to reverse the direction of current in this coil every half a revolution, 180 degrees. This is so that the coil can continue to turn in one direction. Now, in this case, my split ring commutator is left out. So will it able to, therefore, the current in the coil will not be able to reverse direction. Okay, that means the coil may not be able to turn in one direction. Okay, let's see how. When I close the switch, current will flow this way. Current flows. Okay, so AB is this way, CD is this way. So again, if I transform it into 2D, and if I were to place my eye here, I view it this way, I will see AB, I will see CD. Okay, I'll see AB and CD. And because in AB, the current is going from A to B away from my eye, so I will use a cross. In CD, the current is going from C to D. That means it's going into the eye, so I'll use a dot. So when I do this and I apply Fleming's left-hand rule, I find that AB is going to turn. AB is going to move down. The force on AB is down. The force on CD will be up. Okay? That means they will start to rotate. Rotate in the anti-clockwise direction. But once it rotates to the anti-clockwise direction, because there's no split ring, it will just stop there. Okay? Because I will draw how it looks like. You will turn and turn and turn. A, B will be here. C, D will be here. Okay, because the direction is still not reversed. So this is the pivot, and there's no more moment because the force passes through the pivot. Therefore, it will eventually stop there. So answer is C. Okay. Yeah, we are not required to know in detail for split ring, but because this is a new syllabus, I don't know what they will be testing, so it's good that you have some extra knowledge of split ring. Okay, so let us go to a structured question. You're supposed to do question 4, right? Okay, this. Okay, the following shows a wire PQ placed between the poles. There's a current in wire PQ. So when there's a current, it will produce a magnetic field. And when it produces a magnetic field, it will interact with the external magnetic field, which is there. So these two are my external magnetic field. Okay. Okay, so sketch line with arrows to show the magnetic field's direction between the magnet's poles. So they are asking us to do this. So it's going from north to south. Alright, so we have something like this. Now it should be uniform. Okay. And in the correct direction. Now the force on PQ is into the paper. So they give us the force. So the force is into the paper. That means it is into the paper. Now dot and cross doesn't imply it is force, magnetic field, or current. Dot or cross, I say again, represents direction. Direction of what? In this case, the cross represents direction of force into the paper, okay, away from your eye. So explain why a force acts on the wire. Okay, so basically this is what is being given there. When there's a current flowing in the wire, it produces a magnetic field which interacts with the external magnetic field, right? So the keyword here is interact, and then this produces a force. Okay. Now part C, draw an arrow on PQ to show the direction of the current. So in this case, we are given force, which is going into the page, into the paper. So my thumb should be pointing into the paper, and my external magnetic field is going from top to bottom. Alright. So my current will be, the current will be going from left to right. Okay, so this is my current, left to right. Okay, please try it. Okay, now direction of the current and the magnetic fields are both reversed. State the effect on the magnitude and direction. Okay, so since the direction of current and magnetic field are both reversed, that means the direction no change. Okay, and because it's just changing direction of current and magnetic field, the magnitude also no change. What can cause a change in magnitude? Will be a stronger current, because a stronger current produces a stronger magnetic field, so there will be more interaction, and also a stronger external magnetic field, and then there will be a stronger interaction. Okay, but in this case, because the direction of the current and magnetic fields are just reversed, okay, there's no change in the magnitude. So this is question 4. The other question that I want you all to do was question 7. Okay, so it shows a coil of wire connected to a battery, a variable resistor, and a switch. When the switch is closed, the direction of the current flowing around the solenoid is illustrated. So very good, they draw for us these arrows, but if there isn't any arrows drawn on this part, please draw them yourself. This is very important. So in this case, we need to do right hand grip rule. Mark the north and south pole produced in the iron core at X and Y. So still remember right hand grip rule. For solenoid, the fingers represent direction of current and the thumb represents direction of the magnetic field, right? So this is right hand grip rule. Make sure you are using your right hand. So this is my direction of current. Okay, so therefore my Y will be a north pole, my X will be a south pole. Please try it out yourself. Use your right hand grip rule. Okay, next, iron rods functions as a device. What's the name of the device? It is electromagnet. Okay, what is the purpose of having the iron rod? Because the iron is a soft magnetic material. Okay, so the purpose is to concentrate the magnetic field lines and strengthen the magnetic field. Okay, list 2 ways to increase the magnetic field strength of the solenoid. So either increase the current, right, by reducing the rheostat resistance, or having more turns of the coil. Okay, you can look at your notes, it's all in there. Now, a beam of electrons flow through point A in a direction that's perpendicularly out of the page. So this is electron beam coming out, right? And electron flow is opposite to current flow. So if electron is coming out, then I can say that current is going in opposite direction, right? Electron is opposite. Direction of electron flow is opposite from direction of current flow. Okay, so show clearly by an arrow labeled F the direction of the force exerted by the magnetic field on the electron beam. So basically electron beam is flowing, so that means there's current flowing, right? So I would need to use this because Fleming left hand rule uses middle finger to represent direction of current. So my middle finger will be pointing into the screen, and because this is north, so the external magnetic field is this way, right? So my finger will be pointing, my first finger will be pointing from left to right. So and my current will be going into the page. That means my middle finger is pointing into the screen. The force will be vertically downwards. Okay, so if you still don't get this, please ask me when we have our Zoom session. Okay, then I think I asked you all to do question 9, right? But actually we can do this also, question 8. Okay, so this is just for practice, and current is this way. So basically this is our DC motor, so A, B, C, D. So I always like to draw it as a 2D view. Okay, so this is my AB, this is my CD, and also I'm viewing it from my eye over here. Okay, but it's not always that the eye is here. Sometimes the question gives you that the eye is here, right? So doesn't matter, just have to look at the question. For me, I like to see my eye from over this side. Okay, so for AB, because the current is going from A to B away from me, for CD it is coming into my eye, so it is a dot. Okay, so it is quite useful to represent it in from 3D to 2D, so it's easier for me to apply my Fleming left hand rule. Okay, so for AB, my middle finger is pointing into the screen, so the force is this way, and therefore CD will be vertically upwards. So draw an arrow to show a force acting on AB and CD. I've done it. Okay. Determine the direction of rotation when viewed from the front. So yes, so this is from the front. So it will be anti-clockwise. Right. How does the variable resistor affect the speed of the rotation? So the variable resistor can change the resistance to change the current, right? So if I have different current, let's say my current is stronger, my resistance, let's say I decrease it, my current increase, I will produce a stronger magnetic field, right? And because the external magnet doesn't change, I have a stronger magnetic field, they will interact more, so the force will be larger. If the force is larger, then the rotation will be faster. The speed of rotation will be faster. Okay? Okay, so for part D, list two ways to reverse the direction of rotation. I can change. First way is to change the polarity of external magnet. Okay. So north becomes south, south becomes north. Or I can change polarity of the DC supply. Usually now it's plus and minus, plus on the left, minus on the right. Now I can do minus on the left, plus on the right. But we cannot change both at the same time. Only change one because I want to change the direction of rotation. Alright. Okay, so question 9. Unmagnetized magnetic material is brought near to a magnet, is attracted to the magnet. Stay and describe the process that occurs. Okay, the process that occurs is it's called magnetic induction. It is a process where a magnetic material becomes an induced magnet when it's brought near or in contact with a magnet. So magnetic material becomes an induced magnet with the end nearer the magnet having an opposite pole to that of the magnet. Therefore, it's attracted to it. Okay, so don't forget our magnetic induction. And for part B, student is investigating how the force of attraction depends on their separation. He uses the apparatus as shown. Alright, so these are the procedures. So state the relationship between the number of sheets and the force required to separate the magnets. Okay, I'll just copy and paste this answer. Okay, you can take a look at this answer, alright? Okay, then if any question you can ask me. I also upload the answers on Google Classroom, yeah? Okay. Okay, let's move on to other questions. Okay, I think this video will be for all. So if you have any questions about this tutorial, please let me know.